All right, day 2 of limits. We're just gonna continue with what we were talking about last time. So this time we're gonna actually create our own tables though. So in the last video, I had all the tables ready to go. This time we're gonna create our own tables because that's really what we need to be comfortable with doing. So use the table of values to estimate the value of the limit. So it's asking me to evaluate the limit as x approaches -1. And we can see like on this problem that x equals -1 is a place that makes the function undefined, right? So let's look, I'm going to do the tables separately. So I want to approach -1 from the left and from the right. So let's look at like what that means. So I need to think about what kind of values, if I'm talking about -1 from the left, I'm talking about these values that are getting really close. So that would be like -1.1 and 0.1 and 0.01. I'm going to go even further because I want to make sure I can see a pattern in the y values. Sometimes I need to be like all up on top of that -1 value to see the pattern in the y values. You could do more. You could do -1.00001 if you wanted to, just to be extra cautious and make sure you're seeing that value. So what I have here is the limit as x approaches -1 from the left of the function, and we'll evaluate that in a minute. And then I'm going to go limit as x approaches -1 from the right. So I want to be talking about these values. So that's going to be between 0 and -1, right? So that's going to be like 9, 9, 9, 9, 9, 9, and so on. Okay, so what I'm going to do is I'm going to take out my graphing calculator, and I'm going to type the function into my y equals. So you need to be careful to use parentheses around the numerator and then the division symbol, and then use parentheses around the denominator. So I'm going to start typing my equation into my y equals. So I would definitely practice this as you're listening to this video to make sure you're comfortable with it, because if you never practice it and then you have a test question, you might be in trouble. I mean, you're gonna have to practice it in your homework anyways. All right, so let me just double check what I typed into my calculator. Okay, now if you haven't, if you've recently cleared your memory or you've never adjusted these settings, then you're gonna need to go into the table set, which is directly next to the y equals key. So you hit second window. And if you've recently cleared your memory or you've never adjusted these settings, both independent and dependent are going to have a black box around auto. You want to change it so that it asks you for the independent variable. The independent variable is the x. So you need to go down, hover over that ask in the independent column, row, and then hit enter, and the black box will go around that. That way, when you go to table, which is the graph key in the very top right, so second graph, you can type in these x values, which I'm doing right now. And then I can see when I plug in these x values, I get 11, then 101, and then 1001, and then 10,001. And when I punch in these, I get, right? And remember, I mentioned this in the last video. I'm not talking about getting just kind of close to -1. I'm talking about -0.9999999999999999999 forever, right? Well, you can see in the 0.99 table there's as many 9s in the y value as there are in the x value. So if my x value is negative 0.999999999 going forever, then my y value is going to be 9999999 going forever. It's going to be insanely large negative, right? So this limit is going to negative infinity. The closer I get to x, the larger negative the y becomes, right? And you can see the same thing is true, a very similar thing is true in the 1.1, 1.11, or 1.01 t-chart, the first t-chart. It's basically dropping the decimal point from the number. So if I go negative 1.0000000000000000001, then I'm going to have this humongous positive number in the y value. So this is going to infinity, right? So I can say, use the table of values to estimate the value of the limit. I can say that the limit as x approaches negative 1, that's a negative 1, sorry, of this function, oh, that should be a 2, does not exist. The limit from the left does not equal the limit from the right. And not only that, but actually the left-hand limit and the right-hand limits are not defined. So going back to yesterday, we said right here, the general limit only exists if both the left-hand limit and the right-hand limit exist and are equal to the same number. So infinity does not exist. So this general limit doesn't exist. So something I want to show you in this graph, when we graphed rational functions, we talked about asymptotes versus removable discontinuities, holes, right? So I want to show you, and I can tell by the values of these limits, I can tell there's an asymptote at x equals negative 1. So this is the goal. The goal is to be able to, all right, x equals negative 1. The goal is to be able to have a picture of the graph. So approaching from the left, I'm going to infinity, and approaching from the right, I'm going to negative infinity. So that's what those limits are telling me, okay? So now let me show you, let's look at what happens with, so the answer to this question is does not exist. I have the answer boxed, but I want to take this a little bit further. Let's look at what happens when x equals 2. So the limit, I don't remember what the function was. There it is. As x approaches 2. Okay, so we're going to do our t-charts again. We're going to get really close from the left, and we're going to get really close from the right. And I'm going to type those into my calculator. I'm going to go back into my table. And I've got those values, and then I've got those values. So the question is, what does it look like as the x's are approaching 2 from either direction? What does it look like the y is approaching? Hopefully you recognize this number. What is that getting really close to? Well, that's getting really close to 2/3. So this tells me there's not an asymptote because the behavior surrounding an asymptote either goes to infinity or negative infinity. This is going to a number. So what this is telling me is when x equals 2, my y value, I'm going to make it a little bit larger, my y value is going towards 2/3, but I know that this function is not defined at x equals 2. So that's a removable discontinuity. And the way that I would fill in the rest of this graph, well, let's see. No, that's not. I was going to say we could see what happens when we divide, but that would require long division. Actually, hold on a second. Let me do it over here. Oh, it looks like I have. Oh, that's funny. So I had to, this is another video that I had to redo, and I have some of the work over here that I already had. So remember that there's a removable discontinuity when we're able to cancel out the factor like I have right here. That shows up as a hole in the graph. And then there's a vertical asymptote at x equals -1. So let me look. This is equal to that. Oh no, I can't split those up. I thought it was going to be easy. So the way that I could fill in this graph, I know the pieces, I already have some pieces, right? Sooner or later, we're going to learn about, I can't remember when we're going to learn about limits with regard to horizontal asymptotes. And we're going to write some more solid statements about limits with regard to vertical asymptotes. Um, but sooner than later, we will be able to determine the horizontal asymptote from this. You can use your pre-calculus, the things that you have memorized from pre-calculus, but I actually don't even want to encourage that because I want you to learn the limits when we get back from spring break. So what I would do from here is I would just pick like some more x values to plug in. So I would plug in like -2. I'm using my calculator for this. -2 gives me 2. So it's like up here, and that makes sense. And then maybe I go over to like -4 to get an idea of what happens. That's 1.33. So it's doing something like this. I'm not exactly sure. Actually, we should find the horizontal asymptote. Remember the rule about horizontal asymptotes? If the degree of the numerator is the same as the degree of the denominator, then the horizontal asymptote is that lead coefficient divided by lead coefficient. So I've got this. And then I would figure out, like maybe I plug in a 0. 0 gives me something really close to 2. So over 0, up 2. Plug in a 1, I get 0.5. Again, I'm doing this on my calculator. I wonder what happens when I plug in -0.5. I get -1, so like this. So it goes like this. I wonder what happens when I plug in 1.5. This is the beauty of using the calculator. So at 1.5, it's getting close to the 0.67. And then I don't know, I'm just playing around with this. 0.8, what happens if I plug in 5? 0.83, so from here it's getting really close to that horizontal asymptote, okay? So, but we got a lot of features of the graph just from looking at the limits. That's all I want you to focus on, the features of the graph that we're able to get from looking at the limits. So I want you to recognize that this limit, the y values were approaching a certain number, 2/3. Over here, the y values were shooting either up or down, and that's how we knew we had an infinite limit. That's how we knew we had a vertical asymptote instead of a hole, okay? So properties of limits, I would rather apply these than read them off, but one thing I want to point out in the first limit, I'm a typical mathematician, I say this all the time, we're lazy. So it should really be written as two separate properties. Limit of a sum is equal to the sum of the limits, and then separately have the subtraction, but I just color coded them to indicate that the plus always goes with the plus and the minus always goes with the minus. So basically I can split up a sum and a difference. The second one is I can pull a coefficient out in front. The third one I can split up multiplication, and the fourth one I can split up division, as long as the denominator is not equal to 0. So the way that you're going to see this in your homework is they're going to give you values of two limits, and they're going to ask you to find a sum difference, product quotient, something with a coefficient, things like that. So first thing, I'm just going to apply the property from above directly. So I'm copying down that first property, the limit with the difference of the two functions, and then I'm splitting it up into two separate limits. And then from there, I can be like, well, they just told me the limit of f is 4, and they told me the limit of g is -2, and I have a minus in between. So the answer is 6. Same thing is true for B. These are pretty straightforward problems. I'm using the property, which I'll show you in a second, to split up a single limit of division problem into two, this one right here at the very top. So splitting it up into two limits that are being divided. And then again, I know the limit of f is equal to 4, and I know the limit of g is equal to -2, and the question is asking me to divide those, so the answer is -2. Nothing over there. Let's see, are we done? Yep, I think we're done. Oh, I just lost my whatever. Okay, we're done anyways. So big things I want you to get out of this are being able to create your own table. So getting really close to an X value, really close. I'm not talking about like, 1.5 is close to 2. That's not close enough. I need to be really close like I demonstrated in these tables and the tables from yesterday. So being able to create a table to find the value of a limit, recognizing what's happening with the y value, whether it's going to infinity, negative infinity, or approaching a number, and then just being able to apply these properties like we did here.